We will have Domenic Forte with us, who will discuss hardware assurance in a globalized supply chain ecosystem, followed by, in the second session, Helena, Charles, and Jason will discuss and answer questions: what makes a proactive hardware security program successful? To begin with, I'm glad to welcome Domenic Forte, who is an associate professor at University of Florida. He's a senior member of organizations like ACM and IEEE. Additionally, also the committee member of HOST and Asia Host. In today's session, Domenic will debunk common myths and present recent advances in IC PCB reverse engineering. He will also discuss scenarios where reverse engineering can support hardware security and assurance, along with gaps that needs to be filled. Some housekeeping rules for our attendees. The presentation will be for 30 minutes, followed by 10 minutes for Q&A. If you have any questions, please send them across via the Zoom chat. I will moderate them, and after Domenic finishes his presentation, we would answer the questions. Without any further delay, Domenic, I would like to invite you to begin your presentation.
Okay. So I believe you should see my screen now.
Yeah.
Okay, so thank you for the kind introduction, and thanks to those of you who are in attendance today. My presentation, as mentioned, will focus on the benefits of reverse engineering for hardware assurance. So let's start with some motivation. Traditionally, cybersecurity is focused on software and networking, which rely on an assumption of trusted hardware. However, this assumption is no longer accurate. Today, most semiconductor IP and PCBs are commercially designed, verified, manufactured, tested, and transported by multinational companies that rely on one or more untrusted entities. For example, licensing IP cores became very popular in the 90s and is now commonplace today. Today, 3/4 of advanced IC fab capabilities are located in East Asia. And today, many fabless companies are actually outsourcing test insertion and physical design steps to third parties as well. And while the use of these third-party IPs and parties makes hardware design and fabrication more cost-effective, it comes with risks, as you'll see in the next few slides. So hardware assurance is refers to these activities that try to ensure a level of confidence that these electronics function as intended and are free from known vulnerabilities, whether intentionally or unintentionally inserted into the hardware. The most notable risk is hardware Trojans, which are these malicious modifications to hardware designs. A hardware Trojan will typically consist of a trigger as well as a payload. The trigger is designed to fire under very rare conditions, making it difficult to detect it using conventional test approaches. And the payload can act as a remote kill switch, could also cause the IC to leak information, operate unpredictability, or operate outside of the spec. And at an untrusted foundry, it's very easy to insert these Trojan cells to act as both trigger and payload. As you can see in the top right, there's all these locations in the layout which are filled with filler cells, which have no functionality. These can easily be replaced by trigger and payload cells connected using upper metal layers. And again, those filler cells will barely be missed, so it'll be very difficult to actually detect these things. There's also been a lot of stories too with regards to state level tampering, specifically in PCBs and electronic systems, where two methods have been highlighted. The first is known as interdiction. This is where electronics are intercepted when they're being in transit basically to their destination, and they're modified with some backdoors. So a popular example of this was Edward Snowden's allegations that NSA's Tau unit was modifying Cisco products being sent overseas. And the second mode occurs at the manufacturing source and thus enables even greater modifications. The big example of this was, of course, the big hack, the Bloomberg article, which alleged that Chinese spies had implanted a chip, which was the size of a grain of rice and disguised as a signal coupler, into supermicro motherboards. And these motherboards were used allegedly in 30 companies, government agencies, including Amazon and Apple, where they could they had a backdoor which could communicate with remote parties and load malicious codes. And another significant issue in supply chains is counterfeiting. So counterfeiting is a problem dating back thousands of years. And today, electronics are the second most product category that's counterfeited. And that's because the semiconductor industry and electronics itself has really grown in the last 50 years or so. It's been said that around 10% of IT products worldwide are fake, and the cost to the industry is hundreds of billions of dollars in sales annually. And there are, again, a lot of reasons for these horrific trends. So electronics and computing in general have become larger markets. It's desirable to have counterfeiters ride the coattails of successful industries. There are also more devices in the market, such as smart devices and IoT, and that means that there's more waste. And one thing that counterfeiters often do is they bring this waste actually back into the market for a cheap profit. There's also this issue with critical systems and infrastructure, which have decades-long lifetimes. So things like planes and trains have 30 to 50 to, in some cases, 80-year lifespans. So the electronics that are contained in those systems are often obsolete. That is, they're no longer being manufactured by the original manufacturer. And this is yet another way for counterfeiters to take advantage. And most recently, we've had the pandemic, which has created a shortage in all kinds of products, and especially in chips and semiconductors. And this is expected to only really exacerbate the counterfeits in the next few years. And in the area of counterfeit detection and avoidance, the current best practices are to either use subject matter experts to inspect these incoming ICs and PCBs, to procure lifetime buys for long-term system maintenance, or to acquire these from untrusted distributors. And all of these are really non-ideal options. So this leads us to reverse engineering, which is often considered in a harmful light, but today I'm going to argue why it's really the only foolproof way of providing assurance. So on the left side, you can see the harmful applications of reverse engineering, which include identification of exploits, development of attacks, IP theft, and all kinds of things that we've talked about that could lead to failure of critical systems and cyber attacks. And on the right side, you see the positive stuff. So failure analysis, fault isolation, proof of IP infringement, Trojan and counterfeit detection, and one that I'll talk about more towards the end of the presentation, which is obsolescence mitigation. And with that being said, there are always a lot of questions regarding the practicality of reverse engineering. So let me try to dispel some of those things throughout this presentation, especially the blue things that I highlighted here. I'll talk about more, but just here's a gist of it. The first is that people review reverse engineering as destructive, and that means it could only be applied on a per sample basis. But that is changing today, especially for PCBs, as you'll see. There are good non-destructive methods for getting around this. Second, it's also viewed as expensive and time-consuming. And in the past, this was very true, but there are some new instruments, new procedures that are changing all that. And third, traditionally, reverse engineering has been a manual process in one step or another. But it's starting to become more and more automated, both in terms of the physical processes involved, as well as the analysis. And I definitely would expect even greater advances in this in the coming years with the rise of deep learning and AI, which are becoming really popular. And on the right-hand side, I just highlight some of the additional benefits compared to other approaches with reverse engineering. And the first is that it's really the only way of establishing a ground truth for a non-invasive technique, especially if what we're talking about is something that's commercial, off the shelf, or COTS, where you don't have in your possession the original design. It can actually get you the original design. Second, and this is what I was alluding to with the obsolescence mitigation, is that it can be used to recreate, or in fact even upgrade and improve legacy ICs and PCBs. And finally, compared to the non-invasive techniques, it's not really impacted heavily by process variations, which is something that could often mask the effects of Trojans and counterfeits when you apply these non-invasive methods. So the rest of the presentation is going to focus on these advances in automation of PCB and IC reverse engineering, as well as these ethical applications. So let me start with the state of PCB reverse engineering, where our group in particular has made a lot of strides in the last 5 years or so. So we'll start with just the conventional approach, which is destructive. It involves taking your PCB, which is usually a multi-layered structure, first removing the soldering mask to basically expose the copper traces, and then later getting access to the internal layers by delayering, which could be done with sandpaper, Dremel tool, CNC milling, and so forth. And this is where the destructive aspect comes in. And at each layer that you're exposing, the reverse engineer would use imaging, typically optical in the case of PCB. And once you acquire these images, you would process them, denoise them, segment them, etc., to ideally reconstruct the PCB netlist. But there's a lot of reasons why this destructive approach is not so great. For example, if you don't have too many samples of this legacy system, for example, you don't want to destroy the only sample you have. So you'd rather rely on a non-destructive approach. It also means that if you're going to destroy the sample, you can only apply it on a sample by sample basis. So that's where these non-destructive techniques come in, such as the X-ray CT based methods. And by doing this non-destructively, it means that for important high assurance systems, you can inspect every sample. So some of the steps associated with X-ray CT are shown here. First, the sample is basically put into an X-ray CT system where it's rotated. And during the rotation, these X-rays are passed through the sample and collected by a detector. Then these projections are given as input to a reconstruction algorithm, and this returns a stack of basically 2D images or slices, which together form a 3D representation of the PCB. Then the remaining steps are similar to the destructive method, where you analyze this data to recover the PCB. And then using this PCB netlist, you can study or remake it as you want. So in the next few slides, I'll discuss some of the challenges we've encountered when trying to automate the process and how we overcame some of those. So this slide illustrates the first challenge. When the reconstruction algorithm returns a stack of 2D images, each slice may contain multiple data from multiple layers, actually. And this occurs, as shown in the upper left, because the PCB is actually tilted a bit. So that means that when you proceed through the sample in the Z direction, as you can see, you're actually going to get information from multiple layers in each plane. And this effect is illustrated in these portions of the slide as well, where you can see that the actual angle of the sample is again shown in blue, and it's not exactly 0 degrees, which is what's shown in red. And again, as we go through this sample, this is basically one of the Z planes that we see. You can see that in the center, we're capturing data from one particular layer, but on the top left and bottom right, we're missing information because in these parts, we're actually tilted and we're actually in between 2 different layers. So we missed that data. So what we have to do is we actually have to realign this data as shown here. And once we do that, when we proceed through it, we'll actually get all of the same data from the same layer in each plane. So an algorithm that we developed to do this was just an iterative alignment approach, where the center of mass is calculated and then the angle of the center of mass and the origin is basically calculated. Then the sample is rotated and these steps are repeated as shown basically in the middle of the slide until we get the X and Y planes near a threshold of 0. And then on the left and the right, you can see before alignment and after alignment what the results look like for 2 different samples, one on the top and one on the bottom. So in this case, this is similar to the previous slide. You only see information in the center. In the bottom PCB, you only see information in the top end. But after alignment, you can see all of the data from a single layer appears for both of these samples. The next challenge is, how do you automatically identify the layers, how many layers there are, and which slices actually correspond to each layer? And knowing this is very, very helpful and can actually aid in noise removal. Specifically, if you have noise, you could remove that by actually averaging multiple slices together that correspond to the same layer. Having the correct number of layers is also critical in identifying the vias and the traces, because those can actually vary per layer. So this slide kind of gives you an introduction to what those features are that we're looking for, at least inside the board. So the first thing we have are vias, which are these vertical interconnects, which go through the board and connect different layers. There are also different types of vias. So you have through hole, which goes through the entire board, and blind and buried, which only go through some layers. In other words, seeing a via on the surface of the board does not necessarily mean that it's actually contained in the board, like in the case of the buried via, which again is why we need to identify these layers carefully. And then we also have, again, the traces, which are interconnects that electrically connect parts of a layer together. And typically the traces on each layer are very, very different. So as shown in the example on the right, in red, blue, green, and aqua color, you can actually see very, very different traces, and you can see that they're overlapping because they're on different layers. So in order to kind of identify the PCB layers, to align the data, et cetera, we developed a automated clustering mechanism, which groups the slices that correspond to one layer together. And again, it does all this automatically. On the left side, you can see the actual ground truth, which we have for one of our boards, which is a 6-layer board here. And on the right, you can see our clustering results, which match very, very closely to the ground truth. And in the center, we show the quantitative analysis of these results. So we use first the SIFT intensity ratio, or SIR. We use the structural similarity index, or SSIM, and we also use correlation. All three of these have values between 0 and 1. Actually, some can actually have negative values as well, -1. And as you can see here, we all have, for all these different measures, they're very, very close to 1, which indicates high quality. And now for the automated via and trace detection. So for via detection, we developed another iterative approach, which is actually quite elaborate. So I'll take each of these steps one at a time. But first, let me just talk a little bit about the features of this approach. First is that it doesn't require any prior information. It doesn't require any additional data and so on. One thing that we can use, which we incorporate, but we don't necessarily need as well, is the number of classes of vias, that is different sized vias, and what their size range is. But as I mentioned, we could also do without that. We also incorporate some design rules that are typical to PCBs, and use this information along with the class information to iteratively remove false positives. So here's one of our first steps. The vias themselves are circular. So one good thing from computer vision and image processing that we could use is the Huff circle transform, which extracts circles in an image. But as you can see here, which, these extract circles are shown in green, there's actually a lot of circles and non-circles detected here. So we could use, again, that prior information we have on via sizes to restrict the radii range and therefore reduce the number of circles that we detect. And here I also highlighted different colors, which represent the different sizes. Okay, and then once we get into the iterative portion, we're going to try to further remove all those false positives. So the first two steps I show here are the concentricity check, which basically looks at the pixels around the edge of the circles that are detected, and based on their intensity, it determines if there may or may not be a circle. So I highlighted 3 examples here. Number 1 clearly is not a circle. There's a lot of different intensities around the border of this circle, so that's kind of thrown away right away. But in the other 2, you have white pixels, which could be corresponding to a circle or could be corresponding to some other shape, as shown in 2 and 3. And the second step that we use is a radial template match. So we actually try to see if there's actually a circle by comparing it with a radial template, as you'll see. That would actually remove number 3, but keep number 2. So this is what the radial template looks like. It's something that we create in the frequency domain. And this also gives you an illustrative of our iterative approach as well, where initially the radial template looks like this. And as we continue with our steps and we remove false positives, we can actually improve the template and change it over time as shown here. And what that effectively does is it creates a greater separation between the false and true positives in their distribution space. We also do things like mean shift clustering. So there could be a lot of circles that get detected, but they're in the same area. They should be merged. That's what this step does. And then we can incorporate the design rules. So circles that are too close together that would violate via design rules that overlap with each other and so on, those could be removed. We can also take information from the domain. As I mentioned earlier, vias are typically going through the board and at least connecting two layers. So what that means is you could actually take the via information from two different layers and actually check to see if they overlap. And if they overlap, that gives you a higher confidence that a via is actually correct. And if you had blind vias, you could actually remove them because they're not actually in the next layer. And finally, you could do some concentricity checks as well. So for example, as shown here, sometimes you get circles that actually envelop other circles, like as shown here. And in this case, that additional circle is really just showing that there's a layer of dielectric or air that's not conductive, and we don't really need that information. So we could throw it away as shown here. So here's a look at some of our results. We gathered these from both a commercial board where we did not have the ground truth, as well as the smaller board that I showed earlier, which we do have the ground truth for. And I show two methods in the table here. The known column corresponds to the case where we are given information a priori about the number of vias and their sizes. And the unknown information, we don't have that. And I just extracted two layers here from one board, one layer from another board, which are shown in the table. And once again, we use some common metrics, such as intersection over union, which is used for segmentation quite often, DICE, which is a variant of that, as well as, again, the structural similarity index measure, or SSIM. And once again, these values correspond typically between 0 and 1, and the closer to 1, the better the results. So as you can see for this RASC board, we have two layers, and the results are generally very, very high, greater than about 0.85. And as we move to the commercial board, which is shown on the bottom, the results are a little worse because that's a board that was imaged that has a lot more noise, was taken at a lot lower resolution, but nevertheless, the results are still greater than 0.7, which seems quite good. And then if you compare the known and unknown columns, you can see there's very little difference actually between the two across all these metrics, which basically means that our approach that has very little information a priori is comparable to the one with known information. We also recently developed an algorithm that automatically extracts traces. And since this is unpublished work, I won't go into too many of the details. I'll give just a high-level overview. We do some pre-processing, that is to basically segment the image, and we use connected components to extract different components, such as these traces. And then using graph processing algorithms, we actually refine these connected components to make them more accurate, to extract the copper planes, here shown in like this purplish color, as well as these traces. And the cutouts, basically, for the copper planes as well. And for this, we use things like ridge detection to extract these boundaries in a more refined way. And then to apply graph processing algorithms, we create superpixels, which group pixels together for a less dense graph. This makes the processing faster. And then what we do is we actually extract cycles in the graph to actually identify these unique connected components. And based on the size of the cycle, we could break it down more accurately. There's also been significant advances in the automation of IC reverse engineering, which I'll talk about now. So this slide shows the overall process, similar to PCBs. And like PCBs, ICs are these multi-layer structures. But unlike PCBs, there's not yet a scalable non-destructive approach for imaging them, which means that you have to delayer and basically destroy the sample as you're doing your imaging. And then due to the nanoscale features, you can't use optical microscopes anymore. Today, we have to rely on scanning electron microscopes, or SEMs. So showing some SEM images in the slide as well. So in the first step, we need to acquire these images, then we need to denoise them, segment them, vectorize them, annotate, and create the netlist. And an illustration of this process is shown on the bottom for the annotation. So this is a small region of a chip where each of these different regions corresponds to different standard cells or gates. And these are often repeated patterns. So as I show here, NANDs are located like this, buffers are in this green color, and or invert 2-2 is shown in yellow here. And as you proceed and go up in the layers, you can actually start extracting metal, which will show you how these gates are actually connected to one another, and so on and so forth. And from this, you get the netlist. So let me talk a little bit about each of these steps, starting with the deprocessing and imaging portion. So on the left-hand side here, I show the conventional reverse engineering flow, which includes depackaging, and then again, basically taking the sample from multiple stations, wet chemical etching, reactive ion etching, etc. And then bringing it into an SEM to do imaging, and then keep going through this process. This is a messy and error-prone process, which can result in the sample becoming thinner and harder to handle, which means you probably need more samples than just one to do this. In 2017, we developed an automated approach, which is much simpler, and it basically just used two instruments and one instrument for the bulk of everything. First, what we do is we thin the backside to about 1 to 4 micron, and that's done with some backside polisher. And then from there, you just put the sample into a plasma fib sem, which is a 2-beam system. And the first beam, which is the fib, can be used to remove large sections of material from a layer. And then the SEM could be used to do imaging. And using scripting, such as the open platform given by the test scan instruments that we have in our lab, we can actually automate this process and go back and forth between the 2 beams and collect information. So I'll actually show that in the slide here with the little video at the bottom right, where you can see where this again was automated. We're basically removing material slowly, taking images as we go, and this allows us to actually get sub-features between layers. So you can see now we were at just metal 1. We're going to soon be going into metal 2, which is very bright. And then finally, we're going to get to the start basically of metal 3, where it kind of gets bright again. Okay, and again, this was all automated. This could be done in small regions, and then you could stitch those regions together to create the image that you want. But we've also found that acquiring all these images is very, very expensive, very time consuming, especially if you want to do it at high resolution, because you have to do this at different regions and then stitch them all together. So for a modern IC, say a 14 nanometer IC, the process of just imaging alone could take 100 days or more. So it would be great to actually speed this up. And that's what we've done in our work, which we call Automag, which basically takes a low resolution image of the IC and then runs a processing algorithm which determines the regions of high density. So for the 2 images that we have here, the high density regions that are identified by our algorithm are shown in the red color. As you can see, again, there's a lot of stuff going on here. In the areas that are more closer to the center, where we have some metal lines, those are shown in blue, which are less dense. It means that we only need high resolution images in the red regions, low resolution will do in the blue regions. And on a few small samples, we found that we could get 40 to 60% savings in time, which when you're comparing to 100 days is actually a lot of time to be saved. Now let's look a little bit about denoising and segmentation. So for this, we've carefully tried to model all the different sources of noise in SEM imaging and delayering. And we boiled them down to imaging related, material related, and human factors. The imaging related stuff could correspond to the SEM imaging beam, the stage, as well as delayering errors such as uneven delayering. And then for the materials, each material in an IC is actually going to charge differently on the SEM, give you different intensity, which could also create noise. So one algorithm we developed, which is quite interesting, actually makes use of this noise in a very interesting way. So on the top portion of this slide, we see a histogram of the intensity of this image. And on the bottom, we've actually separated it in blue and red, which are corresponding to the background, which is basically silicon dioxide, and the foreground, which is doped silicon. And as you can see, there's a lot of actually overlap in the original intensity image, which means that your normal algorithms are not going to be able to separate these very well. But what we found is actually by exploiting the noise itself actually has a certain texture, we can actually separate these, and that's actually how we did it here. So just to give you an illustration, here's the original SEM image. You can see there's a lot of noise. Here's our ground truth, which we labeled manually. And then we show common algorithms in red. As you can see, there's a lot of segmentation errors, a lot of noise in the areas that are being segmented. And then our laser approach, which again uses the texture and noise to do this, the regions are actually much more clearly defined, especially in this area. We still have some noise in the left-hand side. And then the last thing I want to talk about briefly is actually annotation. And specifically, what I want to say is that there's a lot of excellent commercial tools out there which can actually recognize or use pattern recognition to extract standard cells. But to my knowledge, all of them actually require the standard cell library as a ground truth, which may not always be available. So in our work, we've tried to develop a standard cell detection method which takes no information prior. Just uses some ad hoc rules and some features. Specifically, the features that we use are actually n-grams, something taken from natural language processing, which we found had very high correlation with each standard cell. And specifically the contact layer, as shown here, these square contacts were very, very accurate in predicting what a cell was. So how we encode these n-grams is shown on the bottom left. Basically, the distance between the VDD line and the first column is given by D. The distance between the first column and the second column is given by D1, D2. And then concatenating these things together can correspond to actually a cell. And as shown on the bottom, we use some very simple rules. The intercontact distance rule basically tells you that if you have two distances that are identical for these cells that you have, then it must be the same cell. And the start-end rule basically means that you have to have two cells that are adjacent to each other. If you have anything in the middle, it must be corresponding to a cell. It can't just be some random stuff. And in the table shown here, we see that for 32 nanometer and 90 nanometer, we had quite different results. For the 32 nanometer, which had high correlation with the n-grams, our true matches are very high, 94%, while our failed matches are 6%. But on the other hand, the contacts didn't have as high correlation for the 90 nanometer, so it's a little bit more evenly distributed. Okay, so I know I'm running low on time. I'll try to speed up so we can get to the end. So I want to take a moment to actually discuss how we could actually use this information that's recovered by reverse engineering for hardware assurance. And for simplicity, I'm just going to focus on PCBs, but the same thing could apply to ICs as well. So you could consider lots of different scenarios. The first scenario that I show here is that we have an original design, and that means it's actual CAD file. And if we want to test the PCB, we could run it through our flow, actually generate a CAD file for it, and then we can actually compare those two CAD files. And if there's any differences, it could mean that there's some defects. It could mean it's a counterfeit, a Trojan inserted, and so on and so forth. But the second scenario, we could also assume that we have less information. Like we don't have the original design, but maybe we actually have X-ray CT images from a known authentic board. Again, we could run that through our flow. And in this case, we don't necessarily need a CAD file. We could actually just compare the two images in the image space to find the differences. This could be used to identify defects, which could be, again, consistent with counterfeiting or Trojans. And finally, again, we could also consider the case where we have no prior information at all. This is a commercial off-the-shelf PCB, for example. In this case, we could run it through our flows. And in this case, since we have nothing to compare with, we have to kind of do some analysis on our own. We could try to extract defects automatically, which are kind of known defects, to indicate if it's a counterfeit. We could also create this CAD file, and then with the CAD file, we could also run PCB tools to analyze it. Those could be, your typical commercial tools that look at the reliability of a PCB, signal integrity, But it could also be security analysis tools, which are very few and far between today, but I'd expect them to be created in the future. These are things that would actually analyze the CAD file and maybe indicate that there could be a Trojan because of the way these lines are, things like that. And again, I promised we get to this as well, and that's obsolescence mitigation. So this, again, is a big issue for our legacy infrastructure, our legacy systems. These are things that are scarcely found because they're no longer being produced. So what we could do is we could do a reverse engineering flow, recover the net list of your IC or PCB, and then rather having to go and out and buy a new one, which is going to be very, very hard, because again, they're not being manufactured anymore, you could use this data to actually remake the PCB or IC. And further, you could go even beyond that. You could make improvements to it. So using those analysis tools that I mentioned, again, for PCBs and ICs, you could actually determine if there's any security issues, and the PCB that you remake, you could actually upgrade it, make improvements, remove those security issues. So one example of this could be to create a chip in a new technology node, which is less vulnerable to certain things, or to upgrade the crypto in the system from a DES, for example, from a very old system to AES. And in doing this, you could actually get a PCB that's actually better than the original. And then, of course, you verify and validate it. And so just to summarize and leave some time for questions, this presentation, again, focused on using reverse engineering for security and assurance of hardware. We tried to dispel some of the myths associated with this and showed that for PCBs and ICs, this can be automated. If not now, then very close into the future, it'll be fully automated. And I want to also point out the interesting future directions, which I'm sure you're all want to know about. So the things that I see is, first, this is a multidisciplinary effort. It requires experts in VLSI, PCB design, material science, computer vision, deep learning, and so on. And a lot of these experts don't have access to this kind of data, this kind of equipment. So we need efforts that, for those of us who do have the equipment, to create open source data sets, either synthetic or actually real data sets. This could accelerate things like deep learning, which, as I mentioned earlier, actually requires lots and lots of data. That's why I didn't use too many machine learning approaches, in our approaches. And second, I want to go back to, again, this security analysis. So these tools that could be used to analyze PCBs and ICs, such as the ones from, for example, Tortuga Logic, and I'm sure will be discussed in the panel that's upcoming, those could be used not just for pre-silicon analysis, but for post-silicon analysis as well. By that, I mean, when we reverse engineer our PCBs and ICs and get net lists, we could use such tools to analyze them, to determine if there's any issues, and to improve upon those things. Okay, so before taking questions, let me just acknowledge all my collaborators and folks who have contributed to a lot of the work that I showed here. This includes students, postdocs, engineers, as well as other faculty at University of Florida and WPI. I also want to thank our partners and sponsors for the gifts, grants, which allowed us to get this equipment and do this work. And with that, again, I want to thank everybody and be happy to answer your questions.
Thanks, Dominic. Friends, if you have any questions, please send them across via the Zoom chat. There is a question or a comment, Dominic, I'm not very sure, but I believe it's a comment. Has the Supermicro allegation ever been proven, which was discovered by Bloomberg team? Any response to that?
To my knowledge, it hasn't been proven. Like, nobody has the smoking gun, like the board that actually has this. But after that story came out, and people kind of thought that it was a bit ridiculous, a bit outlandish, that this small signal coupler could actually do all of the things that were stated in the article. People did show that if you had a 2-terminal device using current technology like 14 nanometer, 10 nanometer, you could A, have processing capabilities to do this, and B, if it was inserted where it was inserted in the article, you could actually bypass the OS and actually load in your own OS, change signal communications, and so on and so forth. So it's indeed possible. Whether or not it's been proven or it's been demonstrated to have happened, That's another question.
All right. Any other questions from everybody? Anybody? Let's give them a minute. Meanwhile, friends, if you liked today's session by Domenic, please give him a shout out on social media. Would highly appreciate it. Also, this session is recorded and will be uploaded on the YouTube channel later on for future views. Domenic, I don't see any other question. I see a comment from Rajani. Thank you very much for the very interesting session from our side to you. Okay, well, that's it then, Domenic. Thank you so much again for sharing your learnings and experience with us.
Thanks, everyone.